Hey guys, welcome back to AlgoYogi. We are doing binary search series, and the next problem is maximum candies allocated to k children. So you're given a zero indexed integer array candies. Each element in the array denotes a pile of candies of size candies I. You can divide each pile into any number of sub piles, but you cannot merge two different piles together to basically increase the number of candies at a pile. So you cannot merge, but you can definitely divide one particular pile into multiple piles. You are also given integer k, which basically represents the number of children that we have to distribute these candies to, such that each children gets the same number of candies. So we should allocate piles of these candies to k children such that each child gets the same number of candies. Each child can be allocated candies from only one pile of candies, and some piles of candies may go unused. Okay, that makes sense, perfect sense. So now we need to return maximum number of candies each child can get. Okay, so you can see over here we are given these candies. These are different piles of candies. First pile has 5 candies, then another one, next one has 8, then 6, and k is the number of children that we need to distribute these candies. One student can have maybe just exactly one pile. We can't just give a student multiple piles. Now we just need to maximize the number of candies each child should get. So let's switch the view and understand. Okay, so we have 3 candies here, and then we have 3 students. Now we need to basically give each student same number of candies, and that too we have to maximize the number of candies that we are giving each student. So if you see over here, what's the range of candies that we can give to these students? And that would be actually, so you can give minimum 0 candies to each student, and they'll be happy. They won't be happy, of course, but that's the minimum number of candies that you can give. Then you can give 1 candy, then you can give 2 candies, and then max you can give basically max of these candies, which is 8 candies. But you see over here, you can't really give 8 candies. It has to be something in this range. It has to be something in middle of these range. So you could choose to give 2 candies. If you choose to give 2 candies, that means 2 from here, 2 from here, 2 from here. Or you could easily divide these. You could basically, if you are choosing to divide these, you could have done basically divide that 2 as 2 and 3, and then 8 2 as 2, 2, 2, and 2, and then 6 as like keep it 6, and then these 3 2s you can give to all these students. Okay, but we have to maximize the number of candies. So what we're going to do is, we have this range, so how about we have a for loop starting with 0. Basically we have this for loop. So for let's call it C, candies in range from maybe let's say 1 or whatever, or 0, or maybe like we don't really have to, honestly, 1 to what should be the range? What is max of these, all of these? So let's just call it max of candies. Okay, that would be basically the range of candies that we can give to these students, k students. Now what we want to do is, let's count the number of student we can give C candies. Okay, so let's have this variable called num candies. Initially it would be 0, and then what we are going to do is we're going to go through these candies. So for candy in candies, and we want to basically increment this. So num, we're basically trying to find the number of students that can receive, number of kids that can receive basically C number of candies. So number of kids num kids, I'm gonna just call it num kids with C candies will be basically plus equals to this candy divided by this C, and we're gonna take basically this integer division so that we can have these if let's say if we were trying to divide basically 2 candies each student, so 5 divided by 2 will give us 2 point something, but basically we don't, each pile can only be given to one student, so that will have only basically two candies in total. So that will basically we keep incrementing these number of kids that we can divide the candies from this place. And there might be situation where you're dividing, let's say 8 divided by 2, you're getting like you can divide 8 in 4 students if you're giving each student 2 candies. Okay, so that's the entire logic here. Now if you can see, once you come out of this loop, you'll have this number of kids, and if these num kids are basically num kids are basically greater than or equals to your k, then you can basically what you can do is increment your result to max of result and whatever C that you just chose, so C. Okay, and then you will just come out of this. That's like brute force approach approach that's brute force approach, and that will be basically of time complexity of if there are C number of candies, so big of C, and for each C we are basically in this range from 1 to max candies. Let's say if this number was k and we are doing it from 1 to k, then it will be C into C times k. But we can do better job because it's all about searching within this range. Rather than doing a linear search, we'll do a binary search, and we'll do the same kind of logic to find out that maximized candies, but we'll just do it in the way that we have this range from 1 to 3 to max. In this case is 8. In this case we'll just have our left and right pointers. We'll find out the middle, that would be 4. Is 4 the right number of candies to distribute? Let's find out. So if we give basically what we will do is we'll again use that for loop to basically check if we are able to basically give 4 candies. So we're gonna divide all of them by 4 and add it to the number of kids that we can distribute 4 candies to, and this is our mid, by the way. So we'll actually find out that we were able to divide it by 4. So this 5 gives us 1. 5 divided by 4 is 1. 8 divided by 4 is 2, and then 6 divided by 4 is also 1. So this is the number of kids that we have if we distribute 4 candies into 3 kids. Okay, not 3 kids, this is the number of kids that we have if we divide these candies into some number of kids. That's the number that we're trying to find. So we're distributing 4 candies each student from these candies given to us, these piles that are given to us. And when I'm dividing it, I'm automatically like dividing it splitting those candies. So 8 was split into 2 in this particular case. So this is a number of students that will have these candies are 4. 4 is greater than or equal to 3. That means this is a valid answer, and if it is a valid answer, we'll store it into our result as 4. But we will move our right pointer to we'll move our left pointer to mid plus 1, which will be 5, and that's because we are trying to maximize. So there might be some more number of candies that we should be able to find out that can actually give us 3 students. Right now it was 4, and we will be able to basically distribute more candies. That's the whole agenda. We are trying to maximize the number of candies that we can distribute. So we'll move this pointer to basically 5 plus 8, that will be 13 by 2, 6 will not pass, but then we will come down, right pointer move to 5, and left and right both will be 5, and 5 I think will pass in this case. So the right answer would be 5, because one kid can receive 5 candies from here, another can receive from here, another can receive from here. Given that we split these to 3 and this one we are splitting to 3 and 5, and this one is 1 and 5. All right, so that will be 5 will be our answer over here, and we just went through the entire algorithm to basically get that answer. So let's write the brute force solution and then the optimized solution using the binary search, and we'll also write the time complexity for each of those solutions. Okay, so let's switch the view and let's focus on the code editor. So brute force solution, as we talked about, we're going to have result. Initially, let's have our result to 0, and then we have this range that we are basically trying to find that out. Starting basically, like, you can start at 0 candies, you can start at 1 candy or whatsoever, but at the end of the day we are trying to maximize the number of candies that we can distribute. So let's have this C in range, and range would be basically maximum from candies. Okay, maximum from candies. Now what we want to do is num kids the num kids with we can say C candies. Okay, num kids with C candies. So number of kids, initially it would be 0, but let's try to find out. So for candy in candies, here C is basically the capacity, right? Here C is the not the capacity, the maximum candies, okay, that we are giving to each student. So number of kids will keep incrementing that are getting C candies is by, if we divide basically this particular candy, that's candy pile, I can say this pile, okay, we will divide this pile by what? These C that we have chosen, this C that we just chose basically to divide, okay, by C. All right, that we will add to our number of kids, and then once we basically come out from this loop, we'll have this number of kids, and if this number of kids is basically greater than or equals to that k that's given to us, that means what? This could be our maximum candies that we could divide between among k kids. So what we'll have is res will be maximum of res and C, okay, res and C, and then finally we can just return res. So let's zoom out and submit this answer. Remember, this is a brute force solution, and I hope it passes the test cases, except just this little thing, this division cannot happen by 0, so we'll have our minimum candy as 1. All right, what's happening here? Oh, result could be 0, sorry, my bad. It's this candy that we have to start at that one, that C has to start at 1. All right, so let's try to submit it, and it's definitely gonna fail due to the time complexity, because here in this solution the time complexity is going to be big of n into, basically, if this range from 1 to the max candy is k, so n into k, and for each of that range for k, we are basically again trying to going over pile by pile to find the number of kids that we can distribute that C, that from that range the number of candy that we could distribute, and space would be basically same. Space complexity would be basically big of 1 constant. So now this is our brute force solution, so I'm gonna just comment it out, and let's write down our most optimized version, which is from binary search. So again, we'll have our result as 0, left and right pointer would be basically, left would be 1 and right would be maximum from, we are simply just doing the same thing that we have done here, except this part right outside we were doing a linear search to find this C, we're going to do a binary search to find this this maximum candies. So we'll have this candies over here, maximum candies, and then we'll have our while loop when left is smaller than or equals to right, find the mid would be left plus right divided by 2. Now we are choosing this M as the maximum, basically maximum, this within that range we're choosing this middle value as the number of candies we're going to distribute to the kids. So we'll do the same thing that we have just done over here, num kids, but this will be done linearly, okay, oh my god, this will be done linearly, but except one little change, that this pile that we have will be divided by M now. Okay, and now we're still calculating this num kids with M candies. Okay, so we're changing just a little definition here. Okay, so once we come out of this for loop, we'll have number of kids that we could divide these M candies equally, and if we could not, so we can make a check here. If this is basically greater than or equals to K, that is the number of students we could divide M candies. That means we can set our answer as max from result and this M that we just calculated. And if this is true, then we might want to increment, we might try to find more candies that we could distribute. So we'll just move our left pointer to mid plus 1, else is we couldn't basically divide that number of candies among, we couldn't basically create that many groups. This num kids is basically the group of groups that we could create from the available piles, and if we try to divide these number of candies, so we'll have to bring our range down to basically right range to mid -1. Okay, otherwise I think everything will, okay, I forgot to zoom in here. You can see the code nicely now. So now what we can do is return our answer, that will be return result. Okay, anyway, we'll have to zoom out to show you guys that it should run on the example cases, and it does. Let's submit it. This time, last time it was basically in submission it was wrong because of the time complexity, but this time it got submitted just now. Yes, so let's write down our better time complexity, which is, I'm just gonna simply copy this, whatever we typed over here, and then I'll just paste it over here, and this will be basically, n will remain same, but k is what really decides. K could be really big. Okay, k could be really big, and you can see it over here in the description. K must be really big, 10 to the power 12, that's k. It's way bigger than the length of the candies, and also the values of candies. That's 10 to the power 7. This is like huge. That is definitely the deciding factor, right? That's what was making our previous code like fail, because we couldn't basically bring k to low k. So I think this is all good now. We can now I don't have it like on my AlgoYogi list. I'll add it later and mark this solved, but this is definitely one of the problems that's from this family, Koko eating bananas and capacity to ship packages within D days. So this is from that family, and I wanted to have it like next to those videos. So all right, see you guys later in the next videos. Bye bye.